Hello and welcome. This is Terrence Fagan, and I'm here to take a look at this problem and figure out what we need to do to solve this. We want to apply the moment to this armature, and this armature is attached to this frame OB and this spring AB. So we know, first of all, we know right now that we have M vector is equal to the R vector cross with the force vector. So we start with that general equation. Now, how do we apply that equation to here? First of all, we want to know the moment about O. So that's our starting point. And what do we want to know? We want to know at A. So that's where the force is coming from. So at all points along this curve, this red arrow dotted curve, the force is through A. So we know we need a vector entitled R, O, A. And more to apply that in a second. Second, we need a force now. So hold on, let's take a look. And what this visually looks like is this. So this right here is the vector R, O, A, and that's a vector. So then we need a force. And that force is done by this spring. All right, so we can take a look. I'm going to change the color of this. And that force is going to be in that direction. And what we're going to do is we're going to call that the F of K, and that is also a vector. So we need to figure out what these two look like. So roundabout, I'm going to change these two to black. So in this case, we know the RO vector, and we're going to put it in I and J terms. So what we know is the R vector is the magnitude of R times the X component. The X component is always going to be in the I, and it's always going to be, if we look at a triangle, it's always going to be, doesn't no matter how big theta is, theta could be over here, right? This armature can be over here, and it's always going to be there, so it's always going to be the cosine of theta, and that's in the I direction. That's going to be in the X direction. Plus, you guessed it, the sine, because we're looking at this side, or this side. The sine of theta, and that's in the J. So that's it for the R vector. Now, this changes from 0 to pi over 2, or 180 degrees. But knowing this is it, this is all you need to do for the ROA vector. The force K is another story. So what we can do here is we can say that force of K, and that's the magnitude of this, times the n, or the unit vector, AB. All right. So, well, how do we get the unit vector of AB? So that's another tricky scenario. So we can say that the unit vector NB and AB is equal to the R vector AB divided by the magnitude of the R vector AB. The magnitude of R vector AB. So in this case, we can say that if I put this term in, say, yellow, and I'm going to thicken this up so we can see this in a little more brightness. And we know that from this point to this point is RAB. So what we can do is we can add this vector here, call that negative ROA vector, plus this vector here, called ROB vector. So it looks like this. I'm going to change this back to black. I'm going to change this width to 1 or 2. I think it looks better. We go from there. So we say that RAB vector is equal to negative ROA vector. And we already know what our ROA vector is. So what we can do, but it's a negative ROA vector because this is true. So we have the AO is equal to negative ROA. That's a common nomenclature. So that's how we can start to flip this around. So we know that our AO vector is negative ROA vector plus the ROB vector. All right. So a little bit differently. So we can start to look at this. Now, we already know what this looks like, but what does ROB look like? ROB looks like it's just, there's nothing in the x direction. So it's 0i minus a in the j. So if we were to add them all up, the RAB vector is equal to negative r, the cosine of theta in the I, plus negative r, the sine of theta, minus a, and that's in the j direction. This is all done for the RAB vector. And the reason why we're finding the RAB vector is because we have to find the unit vector of NAB, because that force always is in line with this spring. So more on that. We can say that the magnitude of RAB vector is equal to the square root of the square of each component. So we have minus r cosine of theta I, and that gets squared, plus negative r, the sine of theta minus a, and that gets squared, all square root. Now remember, a is constant, r is constant, but it does vary with this theta. So what we can do now, again, to find the unit vector is just as simple as this. NAB, or the unit vector of NAB, is negative r cosine of theta I plus the negative r sine of theta minus a in the j divided by the square root of this guy. And we're going to call that just, well, we'll just write it out for now, but you can call it whatever you need to. So r cosine of theta, and that's actually a negative, squared plus negative r, the sine of theta minus a, the square root. So that's how you can find out what this unit vector is. Now, that's to solve for this. How do we find Fk? Now, Fk is also varying, so the magnitude is also varying. So we got to come up and take a look at that. Fk is equal to this k times this displacement. And your displacement is going to be different. So it's going to be, I believe we're going to say that some constant XL. So XL is uncompressed length. That's what we're just going to call it. So it's uncompressed length. All right. So with that, that makes things a little more difficult, but not really, because it's back up to this. here is your partial, your displacement. All right, but it's the magnitude of this. All right, so we have the magnitude of this minus this XL. So we can say that the stiffness is equal to this magnitude of RAB minus XL for the uncompressed length. And that's how we would get the force in the K. Now again, you can put in all the numbers, but that's how you get the magnitude of that. Again, then once you put, then you have your forces, and you have your units, and then you have your R vector. You can put together a matrix to supply R, what do we have? ROA vector cross with the force of K vector. And we have the building blocks for that. So, hope all's well and keep asking questions, and I'll see you next time.